Okay, good morning, everyone. How was the evening reception yesterday? I only see thumbs up. That's good. Good job. Everyone is still exhausted. How many of you follow the 25% rule for shared memory religiously? No, that's good. Wouldn't it be nice to be able to change it? Or you have to write the patch. Okay, our next speaker is Ashutosh, and he's from Microsoft. He's a Postgres major contributor, and he talks about how we can possibly share shared buffers in the future on the fly. Thank you. The stage is yours.
Thanks, Andreas. Okay, so let's talk about very interesting topic, something that is being discussed in community, tried many times, and something that we are interested in. So how do we change the shared buffers without restarting a server? Well, I'm Ashutosh Bapat, but the patch that we are proposing on hackers was started by Dimitri, who unfortunately could not come here. So I'm presenting on behalf of both of us. And thanks a lot to Thomas for giving guidance on the slides and also on the patch. And of course, various others, but Thomas helped me a lot when I wrote these slides. Okay, I think this is probably not needed, but I will start with motivation. Why do we want to do this? So the GUC shared buffers controls the size of shared buffers in the shared memory. And when we want to change shared buffers, we need to restart the server, which means that for that, till the time this effect is coming into reality, high availability is hampered. But more important is what we want is the working set to fit in shared buffers. And these days, working sets change dynamically. They change over a period of time. They change during the day. So it's more dynamic than it was previously. And in order for the changing working set to fit in shared buffers, we need shared buffers also to be dynamic, which is not. Every time we have to change the shared buffers in response to changing working set, we have to restart the server, which means that we have to take a hit on high availability. The very reason why we need to change the shared buffers. What happens because of this is people usually set the shared buffers during initial phases of their database design, and they either choose to keep it very high or keep it very low, taking hit either wasting the memory or taking hit on the performance, which both of them is not an ideal condition. And now that we have ML and tools to auto-tune database, it becomes more of a problem because when these tools need to try out a particular value of shared buffers, they need to restart the server, which means these auto-tuning cycles are longer than than these tools expect them to be. In fact, in the literature around these auto-tuning, specifically for PostgreSQL, they mention that just because there are these GUCs which require restarting server, these tools take the pessimistic approach, and for every iteration of their tuning, they restart the server, which is completely against the philosophy of auto-tuning. So let's see. First of all, what I'm going to do in this presentation is I'm going to talk about problems, what problems we are trying to solve, and then also talk about solutions and alternative designs to these problems. This is something work in progress. So we'll talk more about the alternative designs and what design we are leaning towards rather than the final solution. But let's start with what it looks like today and why changing shared buffers is so hard that it has taken, I mean, for so many years we have lived with this problem. Okay. Well, that complexity itself tells something. But so the way PostgreSQL allocates the shared memory is when the postmaster starts, it allocates shared memory and maps it into its own address space. So here, shared memory, which is outside the process space, let's say, and it gets mapped into the process's address space. Then it divides this shared memory into many chunks for different purposes. And I have highlighted some of the chunks which are used for shared buffer management, like buffer descriptors, buffer blocks, I/O condition variables, checkpoint buffer IDs. They are all parts of that shared memory, and there is much more before and after this. And then, for each of these chunks, there is an address where that chunk starts. And that address, it then takes, that address which is mapped in its own address space, it takes and puts it into a shared hash table, which is a SHMM index. So you will see that there is an entry for a buffer descriptor which points to the address space and which really is pointing to the shared memory here. Now, why we have to do all of that is because we want the backends that will start whether they are worker backends or client backends, to know where the shared stuff is, where those shared data structures are in the shared memory. And the way to do that is, when a backend starts, it maps the shared memory block at the same address space as the postmaster. How it does that is a mystery. I won't go into that detail, but just let's assume that it can map it to the same address space in the backend. And once it does that, automatically, rest of the data structures in the shared memory fall at the same address which are shared in the shared index or shared hash table in the shared memory. So now then the process goes, looks up the shared SHMM index table, and gets the address of that block. And that's how it knows where in its own address space it can find the buffer descriptors, buffer blocks, I/O condition variables, checkpoint buffer IDs, and so on. One thing I'm missing here is the buffer lookup table, but we'll see it in a bit. Okay, if you want to further dig into how the shared memory is laid out, there is a PGSHMN allocation view, which gives you the name of the structure, the size, its offset from the start of the shared memory segment, size, and so on. Now, these individual blocks will now go one level down and look at each of these individual blocks. You will see that they are just arrays of buffer descriptor structure, buffer block, conditional variable, similarly checkpointer buffer ID, it's an array. And they are all indexed by buff ID, which is part of the buffer descriptor. So even in shared memory, these structures are held together as vectors. Buffer lookup table, I have shown it like this, but it's also in the form of an array, actually. Because the buffer mapping table, which maps a buffer tag, which is basically the page, to the buffer ID is array is actually as many arrays as the number of buffer partitions, but these are allocated one after the other, so they end up being like almost contiguous. This whole thing ends up being contiguous, and then there is array of entries, which then is linked as a dynamic hash table. Okay, so now probably you might have already understood why resizing shared buffers becomes a problem. Because if you want to resize one of these arrays, it means that all the addresses of the remaining structures also change. If you want to expand that array or shrink that array, the address spaces move. With address spaces, if we want to do that, we have to move the data as well. And since all the processes have the address spaces in their own memory, saved in their own memory, we have to synchronize this change of address spaces. It does not just affect the buffer management, it affects all the subsystems of the database. So we require moving data, it affects subsystems, and then extensions, which also allocate some chunk of the shared memory, will also need to cope up, which means they have to, if we go this route and change shared buffers, they have to also adjust, they should have code to adjust their own address spaces. Now, there is MySQL, which does this, so it's not impossible, but it's a lot of hit. And most important, it affects pointer stability. The address spaces that we have shared across all our algorithms depend upon these address spaces being consistent in the processes. They use linked list, which are pointers, they need to be consistent. So it affects instability. So that will be a whole lot. It will change the way we use our shared memory, the way we have written algorithms, and so on. So it will be too invasive for us to implement it. Any questions till now? We can take one question.
How do you estimate the work space that you use? One moment.
Okay, I'll quickly answer it, but it's a bit out of scope.
Can you repeat it?
When Postmaster starts, it knows how much memory, it knows how many backends, how many buffers it wants to allocate. From there, it estimates the sizes of these different data structures, and then allocates this big shared memory and then divides it. Okay, we'll come back to it maybe after the session. Now, we don't have to go to a point where we start destabilizing the address spaces. The solution that we have proposed basically uses separate shared memory segments for each of these structures, at least for the shared buffers. For the other structures, we might reuse this same solution, or we might devise a new solution. But at least for shared buffers, the solution that we propose uses separate shared memory segments for each of the structures, each of the arrays. And thus, when we resize, we don't need to move, we don't affect the rest of the structures, the rest of the shared memory. We can resize within that address space, within that segment. And that it maintains pointer stability, because the starting address of each of these structures remains same throughout the life of the server. And the other end might move, but that's, the stability of that is not required. So from the first picture, which is like this, a single thing, we go to something like this. where there is still main shared memory, which has other structures, but then we separate shared memory segments for descriptor, blocks, I/O, checkpoint, and buffer lookup table. Now, so the next question is, how do we manage these shared memory segments, and how do we basically allocate them? So the idea here is that we reserve the address space. We reserve the address space, not the memory. So in the process address space, we reserve like a possibly very high memory space, which for each of these segments. And that memory space, that memory map does not change. That reservation does not change. What changes is the memory allocated within that address space as we resize the buffer. So this reserved address space is then divided into two chunks. One is the allocated memory, and one which is the address space reserved for future expansion. And both of them undergo, their sizes, they shrink, expand as the shared buffers are required to be changed. There are two approaches to do this that have been discussed. One is pure mmap approach, which where we use mmap plus memory initialization to allocate memory, and then another mmap to reserve memory. Reserve address space, not memory. The second block, which is white, does not eat any memory. The one which is gray eats memory. And when we want to resize it, we remove the second map, reservation map, change the memory allocation as we required, changing the corresponding map, and then again put back the reservation map in the remaining space of the reserved space. So when we shrink the memory allocation, and when we expand the memory allocation after. So the three steps: unmap reserved memory, remap allocated memory using mremap, and mremap with memory initialization allows us to allocate memory as well, and then map the reserved memory back into the remaining space of the address space. The problem here is mremap does not support expansion with a huge table, and we use huge tables heavily. So the second approach that I think is the current approach towards which we are leaning is to manage the memory allocation using anonymous backing file. I think the name is anonymous backing file or anonymous memory map file, which is mapped into the shared memory. And by changing the size of that file using simply a ftruncate, we change the memory allocated to it. And so there is reserved space map, which is created by postmaster at the beginning of the server. And then when we want to resize the shared buffers, we just do ftruncate on the anonymous backing file. Even though I have showed the white block here, there is actually nothing there. This reserved address space itself is enough to keep that space being reserved and reserved for future expansion. So when we want to shrink, we shrink the file. When we want to expand, we expand the file. Even though we are calling it file, it's actually the shared memory object behind that file which gets resized. Along with ftruncate, we have to use some mechanism to allocate the memory actually. So ftruncate may not always allocate the memory. We have to do something so that the actual pages, memory pages, get allocated here. And for that, we can use fallocate, But fallocate is Linux only, and there is POSIX equivalent, POSIX fallocate, which does not work with SHM variant of the system calls. But I think what we can do, and that's what PostgreSQL does actually, is when we allocate new memory, it initializes that memory. When we allocate buffer blocks, it initializes buffer blocks, buffer descriptors. So when we expand, when we shrink, we don't have to allocate any memory. We just remove, once we f-truncate and shrink, the extra memory is gone. When we expand, we have to write to those pages, initialize those pages so that they are allocated. And if it happens that that much physical memory is not available, then we will come to, we will get the error right at the time of initializing those pages when resizing is not really possible. So I think, and I haven't really tried it on all platforms, is we could get away with fallocate and just rely on the memory initialization. But the problem there is that we will get SIGBUS or some kind of that error instead of fallocate returning us an error. So we have to be better equipped to deal with those kind of things. Anonymous backing file, I have talked about. Other alternative that is proposed, and it's possibly viable, is to use madvice. The problem there is that when shrinking, it does not release the memory immediately, and that memory remains accessible. One can write to that memory, and, well, when that page will be released, who knows what happens to whatever was that written. Whereas with the memory anonymous backing file, if you try to write in the reserved space, like outside the file, then it will give us SIGBUS. So like it's not possible to write into that memory. Okay, so this resizing operation, of course, we talked about how to reserve the memory, how to reserve the address space, and deal with the issues of pointer stability. But there is more to it. That's just one part of the solution. The other part of solution is what to do with the data structures that are in that memory, which need to be shrunk and expanded. So again, there are two cases when we are shrinking buffers. What we have to do is the buffers which are in the portion that is being shrinked, there may be dirty buffers there, or there may be pinned buffers, and we have to take extra care. So dirty buffers we can write and evict, but pinned buffers pose a problem for which I think we have to give few options of whether we want to delay the operation or whether we want to abort the operation, abort that particular backend pinning the buffer. That's something that needs to be thought about, but we'll touch that point again. Then the extra elements in buffer descriptor and IO conditional variables, those we need to empty. We have to remove any data from there. When we evict the buffers, the buffer lookup table entries are also removed, so that happens automatically. The open question for which I still need investigation, or we still need investigation, is what to do with the buffer lookup table. It's a huge, it's a relatively large table if the buffer size is like GBs. So whether we compact that table, or the options are either we compact that table, but that's a hard problem because we have to kind of re-enter all the existing entries in that lookup table, or we decide that anyway we know that what's the maximum address space that we are reserving. From there we can find out what's the maximum number of buffers that we are going to allocate. And so we can put a maximum size on the buffer lookup table, and we always keep buffer lookup table at that size, never shrink or expand based on the shared buffers. Where we will waste some memory, but probably that's like V1 solution that will work. Okay, once we have dealt with the data structures and made sure that they fit into the new size of the memory, we can get rid of the extra memory that is allocated and then publish the n buffers to the whole world. Expanding is relatively easy because the area where we are expanding cannot contain anything, and we only need to initialize the memory. Again, the problem is whether we want to expand buffer lookup table, which is an open problem which needs to be investigated, and at the end we publish the n buffers. Any questions till now?
How do you decide initial size of reserved memory? So not allocated memory, but reserved address space for each buffer type.
If I understand it correctly, you want to know how to resize the reserved space map.
How do you decide how much memory how much address space to reserve, basically, for buffers, for backend processes, and so on and so on?
Well, we hate adding new gooks, but I think we will need to add another gook which says max shared buffers, which users can set loosely based on the virtual memory that they have. Or we could be a bit intelligent and decide that ourselves. I don't know, but that's a difficult question because we have so many structures, and the virtual memory is shared across all the structures, not just shared buffer. So when we decide it for shared buffers, we'll have to be very judicious and intelligent about that.
Okay. You proposed multiple ways to do the resizing. The first one was essentially like unmap, resize, map again. My understanding is that that means we kind of lose the contents of the memory, right? And like, if that's the case, is it really any better than just restarting the server, or like?
Yeah, that's a valid question, and I forgot to touch upon that point. So this is the one that we are talking about, right? Where, let me go here. So the resizing is unmap reserved memory, which means we unmap the white box. It becomes non-existent. But that gray box remains there. We remap it. We call mremap, which does not, mremap with map fixed will not change the address space, beginning address of that block. So that data remains there. It does not wipe out the data. It does not wipe out the data in the new size. Like when we shrink, of course, the shrunk area is wiped out, but not the area that we want to preserve. That data remains same. I'll go ahead. I think we have covered quite a bit, but let me move ahead and we'll take questions at the end. So we discussed how to manage the address space. We discussed how shrinking and expanding affects each of the individual data structures. But there are other processes out there who are accessing shared buffers. What happens to them? We don't want to sweep the world under a process which is accessing that data, accessing the shared buffers, running query, and so on. So, and this is another part where we are, like, the approach that we have taken is pessimistic right now, where we kind of freeze the world and then reopen again after the resizing has happened. But we discussed that there is possibility, if we go by F truncate, that we could leave the world open for some time, and only for a moment we freeze the world and then reopen. But anyway, what I want to discuss in this slide is that there are phases we want to execute. For example, on the right, you will see that there are 1, 2, 3, 4, 5, 6 steps that we want to take. And the colored steps are the ones which are required to be taken only by one backend. We call it coordinator. And the black ones need to be, the steps need to be executed by all the backends. Now, the remap step actually would be redundant if we go F truncate way. That's why even F truncate is attractive, because once Postmaster has put an M map and reserved the address space, during resizing, we don't need to remap the space. We don't need to put another map. And so this step becomes redundant. And then you will see that all the colored steps come together, and they can be executed as a single step. So what we see here, because of this remap step, what we see as 4-phase operation can be shrunk into a single-phase operation, which is much easier to synchronize. But what needs to be considered here or kept in mind is that eviction, if we are shrinking, eviction has to happen before we remap the segments. We cannot, if we remap the segments, then the data is lost. If there were dirty buffers in the area being shrunk, they are lost. So we have to do the eviction before remapping. And the initialization has to happen after remapping, because only then the new memory is available. So that's why I segregated it into 4 phases. If we have to go back to remap method, then we still need these 4 phases. And if we go remap way, then we have to tell Postmaster to remap its own address space as well, because that's how the new backends are going to get their address spaces. That's how they will know about the new address space. So if we go about remap, we have to signal Postmaster, let it remap, and then move ahead with the operation. If we do F truncate, this step is unnecessary, except that the Postmaster needs to know about the new N buffers once the operation has finalized. So there will be some. So the Postmaster here actually introduces an asymmetry which we need to deal with. Okay, we just talked about, so this is about the existing processes which are there in the server right now. But what if a new connection comes while we are resizing? Well, we could block the new backend from entering, but that means there is a user visible effect of resizing. Instead, we could admit it and let it complete the steps that the existing backends have completed, and then continue taking the steps that are remaining. So that for user, it's still a backend that has started, but of course, it won't be able to do anything because it is still attaching to the shared memory. When a backend exits, it's simple, we just ignore that backend. I mean, anyway, that backend won't be accessing the shared memory, resized or otherwise. We can ignore it. It should do what it already does, like on shmem exit call. We might require it to be notified to the other backend, so that if any backend is still waiting for the exiting backend to enter the resizing process, they will know about it. But essentially, the crux is we ignore an exiting backend unless it is the one who is doing resizing, in which case the resizing operation has to fail at that stage. So now, as with anything, there are failures that are possible when we are resizing, and we have to cope up with failures. And we touched upon this point that there might be a backend which has pinned shared buffer, what we do with it. Or BG writer might be scanning the buffers, and it's using its own copy of n buffers. We don't want that to change while it's doing that. Checkpointer similarly might be doing its work. Options that we have is we wait for their operations to complete, the pin buffer to be unpinned, and so on. But then we have to make all the backends wait for that 1, 2, 3, whatever backends. Or we could abort resizing operation at that point and let the user retry. If it's a query, if it's a client backend, we can possibly abort that query, which has pinned the backend, and let the rest of the world resize it, or even kill that backend. But I don't think that we can apply the last two to background writer and checkpointer. Remap itself could fail, like ftruncate could fail, mremap can fail, in which case the options are where the backend where that operation fails has to abort, because rest of the world knows the new map, and that one particular backend does not, that particular backend's address map does not agree with the new map, so it has to exit. And if it's the postmaster or the coordinator, then the operation itself should fail. I mean, we might have to go to a hard failure where we have to restart the server. But the way we are implementing this feature, we tackle the points where failure can happen way earlier in the resize phase, so that it's possible to roll back the resize operation rather than going to a point of no return. Now, the next two questions are more on what's the user experience of this feature. So the first is, how would we trigger resizing? And again, there are options. The first option is we do what we do today, convert these shared buffers into a SIG-hub, PGC SIG-hub, do alter system set, and then PG reload conf. The trouble is we don't want PG reload conf to do this heavy operation of synchronization. Otherwise, all the parameters that are being changed also get delayed and affected. So the current patch, what it does is it basically sets a flag saying that, OK, we have seen that there is a request to resize the buffer, but we are not going to do it in PG reload conf. We'll do it later. So once the PG reload conf finishes in postmaster recognizes that this flag has set, and it kicks off this synchronization across the processes. And but of course, there are problems here. Well, every alternative that we have seen has some problems that we need to tackle. There is no single solution which is, wow, this works. So, well, it's an existing interface. So very good, we know what to do. Users are familiar with it. Nothing new is required to be invented in the user interface. But the problems are that a user has very limited control over when actually the resizing happens. It does not easily know when the resizing has ended, and n buffers is published. The new value of n buffers is published. The failures get logged to server error log, and cloud People hate to look at the server error logs when failures happen. They want it on their screen. So somebody needs to monitor the server error log. Similarly, the whole process is not visible to the user. What is happening? If it takes time, what's happening behind? Why it's taking time? Nothing is known to the client. And if a failure happens and we have to retry, when would we retry? How long we retry are the questions when we let the postmaster or the system deal with automatically. And if the retries are persistent, we need user intervention ultimately. I mean, I can compare this with the logical replication failures, where it keeps on retrying, putting something in the server error log, and then after a while, when the wall builds up, people go there, find out the problem, and they fix it. We don't want that to happen here. Well, at least that's my take of it. So the alternate solution here is we invent something new. We give control to the user, and they decide when to trigger this operation. So the first solution here again is alter system set. It changes shared buffers. PG reload conf reloads that, but it keeps it pending. It does not reflect that change immediately. And then we provide a SQL function to start triggering that operation. Well, it seems hacky, but it will work. It works. Actually, I have a prototype where it works. But maybe a more sophisticated way is to change alter system, add a new command, subcommand to it, and say alter system update shared buffers to blah, blah, blah. And then update actually takes responsibility of performing the whole resizing operation and synchronization. Well, the problems that we see with the reload conf are gone. I think since we are changing the user interface, we are changing SQL. I think that seems to be the only problem. And there are some and with SQL, I mean, one problem that we discussed yesterday was, what if user says alter system update shared buffers, it takes time, and then they do PG backend kill or cancel the query. What do we do in that case? But anyway, that's something that these kind of failures we have to handle anyway. So probably we will be able to handle that, the query cancellation also gracefully. A related question is, who takes the responsibility of synchronization? In reload conf, it's the postmaster. It's natural, because reload conf sends first signal SIGHUB to postmaster, then postmaster sends it to all children. So postmaster is a natural choice here. And that's also one which has set up shared memory initially. So it's, probably emotionally suited to use postmaster as coordinator. But then postmaster in Postgres has very limited functionality. It cannot wait, for example. And when the synchronization happening, there is no way that postmaster waits. It has to poll, which means we end up doing like CPU execution or some delayed responses. The second is client backend, where we use, the SQL command that we talked about, the very backend where that command was executed takes the responsibility of synchronization. And it has all the infrastructure to do waiting and synchronization. And then the postmaster spatial treatment is also not required if we use ftruncate. Otherwise, that asymmetry is something we deal with. Or something that is being discussed in wall level change is using a separate backend. I forgot the name of that backend. There is a specific name to that backend where we delegate, where the postmaster or somebody delegates it to them. Okay, I'm going to just mention this and not go into the details, but all these system calls, we need to, I mean, they are not available everywhere. They are available on Linux, but we need to, like FreeBSD, I think supports all of them, not other BSD variants. Windows is a special case where I think all of what we are proposing is doable in Windows, but we need to we need to try and find out. So it might happen that, as is proposed on Hackers, that we might release this solution only for Linux and then go to other platforms. And then multi-threading, the talk we had that same time yesterday, where the whole concept of shared memory will vanish. There will be this huge global heap memory that will be available. But I think we will still require the memory mapping, where we find these structures, and resizing those huge structures using malloc may not be doable. Like, we are talking about GBs of memory. So we will still need some of the things that we are talking about. If not shared memory, the memory mapping, address space reservation. Maybe we'll not need, we'll need address space reservation, and then we will use the files, anonymous files, to manage or allocate the memory. Okay, with that, I have managed to finish this topic, which is large. I was a bit worried that I would overflow the time, but yeah, I have managed it. So we have some time for questions.
3 minutes. Any questions? Here we go.
Yeah, you referred to remapping or resizing and incoming connections. On that slide, you said something like it is fine to let the backend start regardless and then start in the resizing process. Wouldn't that be a stuck backend from the client's perspective?
Would that be, sorry?
From a client's perspective, if your backend is not going through the process of actually doing the authentication, which frequently requires page accesses and buffer accesses, wouldn't it therefore be a stuck backend or a stuck connection from the client's perspective?
Okay, if I understand it right, what you are saying is that backend will connect. I mean, it will start, the connection will happen, but it won't be able to do anything at that point. Yes, that's a possibility. Although the amount of time, I mean, the phases look like 1, 2, 3, 4, but the amount of time is not that long or probably noticeable. And anyway, the new backend has to attach itself to shared memory and set it up, which happens in a new backend. So I think what we are losing is not significant or noticeable. If we give control to user to decide when to resize, I think it's simple, because then they can control whether their applications connect to database or not. But yeah, I agree that that's a problem and something that we need to keep in mind, measure, and see whether it's within acceptable ranges or not. Yep.
Time for one more question.
Increase your shared buffers, and you don't have enough reserved huge pages. How will it handle that scenario? Because right now, like, if you try to start up the instance with on huge pages and you don't have enough configured, this instance doesn't start up. So how would this be handled in this case where it's online?
Okay, I have done some experience with huge table, but not this particular. Yeah, please go ahead.
That's why he included the fallocate step. That would fail. And like if you don't do that, then later on, well, then you might have other problems later on. But if you call fallocate, it'll fail with enospace or mem, whatever it is. I've forgotten. I think it's enospace from huge table fs. And then the operation will fail with a nice error and kind of roll back the operation. So you can try to increase memory size, and if Linux tells you there's not enough huge pages, then it fails nicely, gives you a nice error message, and then you carry on with your life.
But I suppose if we have a gun for reserving the address space, then that could drive the huge page decisions, right? Like initially, like on startup. Basically, you should reserve enough huge pages to accommodate for the reserved address space that you.
Yeah. So I think that's a valid thought process. What the problem is that when let's say somebody starts with a very small machine, right, which has, let's say, a few GBs of memory. They set shared memory size to few MBs, but they still can reserve a large address space. And if we try to test whether that much memory is available, it will fail. So we will never be able to start a server at that point. Later, when they expand their machine, allocate more memory to machine, they can do the resizing and it will succeed. So what you are saying is safe, but may not be practical, especially in the Elastic Server scenario.
I need to move your discussion to the hallway track. Thank you. When you leave, you have QR codes for the feedback on both doors and up here. So please leave feedback. Thank you. And did you take one already? You have one? Okay. Thank you. Thank you.